Hi, I'm Prof and welcome to Chemistry Matters, and today we are going to be talking about phase diagrams. So, in a previous video we talked about the three common states of matter: gases, solids, liquids. We talked about the defining characteristics of solids, gases and liquids, the fact that solids don't flow, gases and liquids do, etc., etc. And then we talked about a couple of defining characteristics of liquids, the fact that they have surface tension and that they also have got vapor pressure. So in other words, above the surface of any liquid are gaseous molecules of that liquid, or indeed gaseous atoms, okay, depending on the liquid. So today we're going to talk about phase diagrams, and these are diagrams that show essentially the conditions under which phase of a sample is stable or is the most stable, okay? So let's get into it by looking at a generic common or garden phase diagram. And this is what such things look like, okay? So first up, a phase diagram is essentially a plot of pressure against temperature, okay? So that's the number one thing. And within the plot, what we see are shaded areas which correspond to the conditions of pressure and temperature under which solid, or the solid form of the substance, is stable, here in blue. The liquid form is stable in green, and the gaseous form is stable here in orange. Okay, so solids, liquids, gases. Now, these phases are divided by lines on the phase diagram, okay? So here you have a line going up like this with positive slope, a line there, a line there. There are also points on the phase diagram, and in this case here, there's a point here. This is a special point that we're going to talk about in a minute, and also a special point out here that we are going to talk about as well. Okay, so essentially what have we got? We've got something that we can look at essentially and say, right, under this condition of pressure, this condition of temperature, we know that, for example, the liquid phase is stable under those conditions. Okay, so there's an awful lot of information on a phase diagram. Now, generally what we're interested in is what's happening at atmospheric pressure, because that's the sort of pressure situation under which we all live. Atmospheric pressure being 1.013 times 10 to the 5 pascals, which is helpfully labelled on here. So let's imagine what happens if we keep our pressure constant and we start increasing our temperature. And you all know the answer to that. You all know what's going to happen here. We're going to keep our pressure constant, we're going to start with a solid form of a particular substance, and we're going to increase the temperature. Well, obviously, your solid's going to melt. If you keep increasing the temperature, your liquid that's got formed from melting the solid is going to boil, and it's going to turn into the gas. And we depict this on a phase diagram along our constant pressure line here, okay? So here's temperature along this axis. We're increasing in that direction. We start off with our solid. We heat, we heat, we heat, we heat, and then it gets to a point where all of a sudden it starts to melt. That point there is called, ta-da, the normal melting point. Normal meaning at atmospheric pressure, essentially. And so at that point there, all of the solid melts, gives the liquid, and then we keep heating. And so we heat, we heat, we heat, we heat, and then the liquid starts to boil and turns into the vapor. And then we keep heating, 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 and all we do is increase the temperature of the vapor. So that's obvious. That's, you know, that's something that you're all familiar with. Melting of a solid, boiling of a liquid. So therefore, we could carry out the reverse process as well. Obviously, we could start with the hot gas, we could cool it down to a liquid, and then we could cool it down to a solid. And again, you're familiar with all of those. Those have got particular names: melting and freezing. You're familiar with that. Vaporization or boiling, and condensation. Okay? Vaporization when we're going this way, past the normal boiling point. Condensation when we're going this way. Okay. Now, what you might not be familiar with is the fact that for some compounds, simply increasing the temperature of the solid, you can go straight to the gas form. And you may possibly be familiar with that. The best example of this is a thing called dry ice or solid carbon dioxide, okay? And with solid carbon dioxide, what happens is you go directly from the solid to the gas without going through a liquid phase. And that is a process called sublimation. So we say that dry ice sublimes, or we could go the other way. We could cool down gaseous CO2, and at atmospheric pressure, we would see that it deposits. That's deposition, and it turns into solid CO2, solid dry ice. Okay, the special points on the phase diagram, this is one of them. You can see that this point here is at the intersection of 3 lines on the phase diagram. This is a thing called the triple point, surprise, surprise, 3 lines, triple point. And at this point here, the solid and the liquid and the gas phase all coexist in equilibrium with each other, okay? So that's a special point, and again, that is the pressure and the temperature of triple point is peculiar to each particular substance that you have got, okay? And another special point out here on the phase diagram, a thing called the critical point, the critical point. And this is interesting because we've got a line here that is the equilibrium line between liquid and a gas. At any point along this line, you're in equilibrium between the liquid and the gas. Essentially, you're boiling all the way along that line until you hit this thing called the critical point, and then something happens because this line now stops, and you are now in the region of a thing called a supercritical fluid. And that's a weird thing. Okay, so some would argue this is a different phase of matter. How do you make a supercritical fluid? Take a closed container, put some liquid in there, and heat it, okay? And when you heat it, the liquid starts to boil. But when the liquid starts to boil, the pressure inside your container gets higher and higher and higher, okay? And you eventually get to the point where the cutoff line between the liquid and the gas form of your substance disappears. And there you have got a thing called a supercritical fluid, which has got the properties of both a liquid and a gas, but which is in fact neither. Okay, pretty weird stuff. So let's then have a look at a couple of real examples of phase diagrams, real life examples. Here is the phase diagram of water. Okay, and again, you'll be familiar with this. At atmospheric pressure, we know that water melts at at a temperature of 0 degrees Celsius, and that it boils at a temperature of 100 degrees Celsius. Less than 0 degrees Celsius, obviously we're in the solid phase. Between 0 and 100 at atmospheric pressure, we're in the liquid phase, and hotter than that, we are in the gas phase. The weird thing about the water phase diagram is that this line here, this equilibrium line between the solid and the liquid phases, has a negative slope. So in other words, as the pressure increases, the melting point of water decreases. Okay, and that's extremely unusual. Okay, and that's why ice skaters can skate. Okay, they exert a very, very large pressure on the ice with their ice skates, and what that does is to actually melt the ice under the ice skates, and so they're skating along in a very, very thin film of water on top of the ice. Okay, so there's your phase diagram for water. Triple point here, 6.1 by 10 to the 2 pascals, so very low pressure, and confusingly 273.16 Kelvin, which is 0.01 degrees Celsius above the melting point at atmospheric pressure, okay? So you get a very, very low pressure and 273.16 Kelvin. You can have solid and liquid and gaseous form of water all in equilibrium with each other at that triple point, okay? I mentioned earlier about CO2, about carbon dioxide, and the fact that carbon dioxide sublimes at atmospheric pressure. So this is now the phase diagram for CO2. And so we look at this here. Here is atmospheric pressure. 101.3 by 10 to the 5 pascals. Your blue, as usual, is the solid, your green is liquid, and your orange is gas, okay? So we look along the 1 atmosphere line here, the atmospheric pressure line, and you can see you go directly from the solid to the gas form, okay? The temperature at which that happens at atmospheric pressure, 195 Kelvin, okay? About minus 78 degrees Celsius, okay? And you will get CO2 converting directly to solid CO2 converting directly to gaseous CO2. A really nice example of sublimation. Okay, now there is way more to phase diagrams than what I've told you, but this acts hopefully as a good introduction to what's going on with these things. It's important to, I guess, know the important points on a phase diagram: your normal melting point, your normal boiling point, the triple point, the critical point, those things there. It's important to realize that at any point along a line on the phase diagram, you are in equilibrium between the two phases, between the solid, the liquid, the gas, or the solid and the gas, okay? And always nice to go to atmospheric pressure and see what happens as you increase the temperature at a constant pressure, okay? And again, a lot of those examples you'll be familiar with and will be able to rationalize by using the phase diagram. Okay, so I think that's all that we need to talk about phase diagrams, and we will therefore see you in the next video.